Hey folks, we're back with the next kinematics video, and this time it's on freefall. Freefall is a special case of constant acceleration motion. So freefall is basically when things are flying through the air. It's defined as any situation where only the pull of gravity influences an object's motion. We'll talk a little bit about air resistance and drag throughout the course, but for the most part we're going to ignore that and assume that when something is in the air, gravity is the only thing that has an effect on its motion. We are going to make the assumption that the force of gravity is constant when we're near the Earth's surface. We'll talk a little bit about the truth of the matter, that the force of gravity gets weaker as you get further from Earth's surface in another unit. But for now, all of the things that we're going to analyze take place near Earth's surface or on it, and so gravity is relatively constant there. What this means, and another part of the course, is the relationship between force and acceleration, is that anything that's flying through the air has a constant acceleration downward because gravity pulls things downward. That you'll be tested on that when you do problems because objects might be going up or down or sideways, but they will still have a downward acceleration due to gravity no matter what they're doing. The way that we talk about the strength of gravity is to talk about the gravitational field strength. We don't get too much into it in this course, but we talk about the fact that it exists in space and everywhere. And so the value for Earth's gravitational field strength is a lowercase g that we will call little g for the rest of the course. Its value on Earth's surface at sea level is 9.81 newtons per kilogram. So it's a ratio of how much force is exerted by gravity on an object per kilogram of its mass. We will focus on these units later in the course, but they are the same as meters per second squared, which is the unit for acceleration. So the gravitational field strength of Earth causes acceleration. We arrive at our key idea in freefall is all objects in midair near Earth's surface have a downward acceleration of 9.81 meters per second squared. That word downward is very important. So we're going to solve some problems, just two problems to get us started in using freefall. First one is the simpler one. You release an object from a large height. What is its speed 7.7 seconds later? So a picture can be very helpful. And so maybe you're standing at the top of the bleachers or on the Grand Canyon, you're going to throw a basketball off, whatever. And you release it, and it travels downward because it's pulled by gravity. Again, we talked in the last video about like the language being important. You release an object. That means that the initial velocity of that object is 0 meters per second. Now, 0 doesn't have a magnitude. It has a magnitude of 0, and so it's a vector. We don't know which way that vector points because it doesn't point anywhere. After this, we have to make some decisions. You release it from a large height and it falls. Now that means it has an acceleration and we have to make a decision. Now, I think up until this point, every decision you've made is that to the right is positive. We're going to add to that in free fall for now, up is positive. What does that mean? That means that any vector that points up and we give it a positive value. That means any vector that points down, we give a negative value. So the acceleration that we're going to use is negative 9.8 meters per second squared. You might notice that I left the 1 off. Later, I'll even leave the decimal place off, and we will round that to 10. The College Board suggests for many problems that you use 10 for little g, just because they don't want you diving into your calculator as often as you might need to when using a textbook problem. So acceleration is going to be negative 9.8 or negative 10 if you want to use that. And we want to know its speed 7.7 seconds later. So the time is 7.7 seconds. Time is a scalar, so it's always positive. And we are looking for its speed. Now, speed is the magnitude of velocity. So we are looking for the final velocity, and then we're going to convert it to a speed. I pick from the same set of kinematics equations, and so I'm going to pick the first one, Final velocity equals initial velocity plus acceleration times time, and then we will go ahead and solve it. Looking for final speed, that equals 0 meters per second plus negative 9.8 times 7.7. So the math on this one's pretty simple. It only falls downward, so negative 9.8 times 7.7. And so I get a velocity of negative 75.46 meters per second. So I'm going to round that, and then I'm also going to convert it to a speed. Speed is the magnitude of the velocity. It's essentially the number without the sign. So my final answer is going to be 75.5 meters per second. And so you can round to whatever decimal place you want. I went for the tenths place because that's where 7.7 seconds is rounded to. Strictly speaking, for sig figs, the answer would just be 75. You'd round it to the whole number because 7.7 seconds only has 2 sig figs. Okay, the other problem is a little bit more complex, and we'll get to it. Okay, so example number 2. You toss a ball upward with an initial speed of 12.5 meters per second. How far above the release point is the ball 1.5 seconds later? So again, a picture can be very valuable. So you take the ball, and you're standing on the ground. You toss the ball upward, and the ball is just going to go up, and it's going to come back down. So the initial velocity is directed upward, but because of gravity, this object is accelerating downward the entire time. So let's look at our values. V naught, initial velocity, is 12.5. Now that velocity was directed upward, and so that's going to be a positive 12.5 meters per second. Once it's released, it begins to accelerate downward, and so the acceleration is going to be negative 9.8 meters per second squared. And so those vectors point in opposite directions. It's moving upward, but it's accelerating downward. And then we have a time of 1.5 seconds. Now the question is, how far above the release point is the ball? So how you identify your unknown is kind of up to you. We're actually looking for displacement, because that is how far away from the release point we're looking for. Or you can just be solving for final position. And we'll talk about this one first. So solving for delta x, because you're looking for how far above it is. But the equation on your equation sheet is written a lot like this. And what we want to understand is that when we're looking for like how far above the release point, we're not told where the release point is. So we're going to make the assumption that x naught is equal to 0. And we're going to solve for final position. So here's how that goes. Final position equals 0 plus positive 12.5 meters per second times 1.5 seconds plus 1/2 times acceleration, that's negative 9.8 times 1.5 squared. If you have a graphing calculator, or even if you have a scientific calculator, you should be able to just plug this in all at once and have your calculator do the rest. If you would rather do everything piece by piece, you are welcome to do that. I find it easy to type everything in situations like this, because then I don't have to like round anything or copy and paste anything. My final position is 7.7 meters. And so this is the displacement. This is how far above the release point the ball is after 1.5 seconds. And so those are some intro freefall problems. We'll probably go through a couple in class, because this is often confusing at the beginning for students. But that's hopefully enough to get you started thinking about it.